So today we'll learn about graphs of functions of two variables. First off, let's think back to one variable calculus where we had a single independent variable, which we usually called x, occasionally t, and then we had a dependent variable, which was usually called y. And we could define some functions, right? So we could say y equals f of x, right? And define, in that way we could define a relationship between the dependent variable y and the independent variable x. And let's say, for example, we had f of x equals x squared. This would define some graph that we could sketch out on the two-dimensional axis. Now for 3 dimensions, we're going to need a 3-dimensional axis, and we'll have two independent variables. So in multivariable calculus, right, so when we're working in 3 dimensions, we'll have x and y as our dependent variables, and we'll have this third variable, which we usually call z, which will be an independent variable. And so we'll have a relationship such as z is equal to f of x and y. And maybe we'll just do a quick example here. Right, and we'll write that the definition of f is 1 minus x squared minus y squared. Okay, so let's start thinking about some possible values of x and y and what would be the value of z. So if I choose x equal to 1 and y equals 0, you can see that when I plug those values into, when I plug those values into this function, I will get z equals 0, right? And so here I'll go ahead and draw this, and it's the purple dot along the x-axis. The point 1, 0, 0 lies on my graph. Similarly, if I plug in x equals 0 and y equals 1, right, the value of the function is 0, and so I will also have the point 0, 1, 0 on this graph. And finally, if I plug in both x and y equals 0, so I'm at here the origin of the axes, you can see that the value of z will be 1. And so I also get the point 0, 0, 1, 1 on this graph. And if I go ahead and plot out everything for all of the values, right, what I'll actually get is part of a sphere. Okay, I'll get a piece of a sphere, and this comes from the fact that if x squared plus y squared plus z squared is equal to 1, this defines, and we'll learn later in the class about implicit function, but this is right. So this equation defines a sphere. Okay, and so we're just right now what we're doing is we're plotting a little piece of the sphere, and but it brings us to an important point, which is in regard to domains. So the domain of a function f of x, y, the formal definition is the set of all points, right? So the set of all points x, y, such that f of x, y is defined. Okay, and so for the function we have, we can, we've picked out some points in the domain already. So the point, right? So the point in the domain lives in the xy plane, right? It's not up here. So the domain is the set of x and y that we can plug in, and we've seen that the point 1, 0 is on the domain, and 0, 1 is part of the domain. Okay. On the other hand, if I were to plug in x equals 0 and y equals 10, if I were to plug these into, right, my function here, I would get the square root of minus 99. And at least in our class, we're dealing with real numbers, right? So that's not defined in the arena where we're working. Okay, so that is the point 0, 10 is not part of the domain of the function f of x, y. And if we wanted to define the domain of this function, right? So the domain of this f, you can see that it would be the set of points x and y such that x squared plus y squared is less than or equal to 1. In other words, we have a circle in the xy plane, and if we were to go ahead and plot f over that entire domain, what we would end up with would be a function that's like a dome. Okay? All right, so that gives you a little, just a little idea of how to plot functions. Now my drawing skills are not sufficient that I can show you all of the wonderful types of functions that you can plot. So I often use computer programs to help me with that. And my favorite for plotting surfaces is a function called QuickGraph, and it's available for the iPhone and the iPad. I gave a link on the course website to something that you can also use for Android, and there are online options as well, such as Wolfram Alpha, that you can just use online from any kind of device. And maybe you have your own favorites, but I'll use QuickGraph for demonstrations in this class. Okay, so we already learned about planes, right? So we'll consider planes as one of our fundamental shapes in this class, but we don't need to revisit what a plane looks like just yet. But let's think about just the next step up in complexity, which would be quadratic functions. So things that have x squareds and x times y and y squared in them. Okay, and let's just go ahead and plot one of those. So at the top here we have z equals x squared plus 4y squared. All right, and if we go ahead and plot, and note that the domain of this function is the entire xy plane. There are no values for x and y that are not allowed. Okay, so we can go ahead and plot, and you can see what this function looks like is a bowl. It's kind of like the it's like the two-dimensional version of a parabola, right? If a parabola is a one-dimensional curve, this is a paraboloid that's a two-dimensional surface. Okay, so that's pretty simple. All right, so and you get that kind of a graph where you have something times x squared plus something times y squared. We'll see in a moment that there are other formulas that can give you a bowl-like function, and you'll learn how to figure out what the shape of the function is. Okay, but that's a relatively simple function, right? Another type of a quadratic function that we can have is, the example is given by x squared minus y squared. Okay, so here, we have x squared terms and a y squared term, but one of them has a positive weight and one of them has a negative weight. And this type of function, what you end up with is a saddle, right? So you have the function curling up in one direction. In this case, as you increase x, right, you see that the function goes into the positive, in a positive direction. And as you increase y, you can see that the function goes in a negative direction because the coefficient in front of the y squared term is -1, right? And this is another one of our fundamental shapes, and we'll call this function a saddle. All right, and then the third type of kind of a fundamental function that you can get by mixing, x squared and xy terms. We'll call that a canyon. Okay, and you can see an example here is given by the function z equals x plus y squared, so quantity squared. All right, and so you can see in one direction that this function curls upwards, and then in the other direction it's quite flat, right? Okay, so when we're trying to visualize, so many people have problems trying to visualize, how to graph these functions. And a useful tool, so something, and there's a bit of, there's a bit of a discussion of this in the book, is to think about slicing through, right? So going back over here to our whiteboard, right? So if we want to, we can think about, say, fixing one variable. Fixing one variable, and then we would vary the other one. In other words, what would it look like if we did something like this? Z is equal to f of 1 comma y, right? So we fixed a value for x and we're going to let the value of y be variable. Or, right, so this is a slice through x equals 1. Right? Or we could do z is equal to f of x comma 2, and this is a slice through y is equal to 2. Okay? And if we go back to our graphing software, and let's go ahead and pick our saddle function. I think that's probably the most fun one. Okay, so now we have our saddle function. And before we even think about what these slices look like, let's think about it algebraically. If I were to fix a value for x, say equal to 1, right, I would get the formula z equals 1 minus y squared, right? So that's a quadratic graph, right? That's a parabola. And similarly, if I were going ahead and fixing y equals 2, I would have z equals x squared minus 4, right, which is also a parabola. They sort of point in the opposite direction, but both give a parabola. So if I want to think about these slices, now I can think about it visually, right? So let's just go ahead and pull up a plane here. And what I've done in this case is actually to make a variable parameter. So in this class, when you see something up in this program that uses n actually is a variable parameter. It's not an independent variable in the sense where x and y is. Think about it as a coefficient that we can tweak, right? It's a constant that we can tweak in order to change something about our function. Okay, and in this, right, here what we're doing is we are taking slices through fixed values of y, right, and we can vary them and we can see that they all look like, right, these degree 2 functions. And if we wanted to change that, we could do essentially the same thing, right, and take slices in x, and same thing, right, now the parabolas, right, point in the opposite direction. They have negative values instead of positive ones. But you can see that as we slice through this, right, that we're getting all of these degree 2 functions. All right, so now we understand some simple functions. Like locally, all of our functions will have the shape of either a plane, a quadrat, a saddle, a bowl, or a canyon. Right. So in the same way that when we looked at derivatives and second derivatives in single variable calculus, we could define any even complicated functions locally. We could approximate them with simpler ones, right? Simple quadratics. And that will be true in multivariable calculus as well. Now, the fun thing about multivariable calculus is you can define much more interesting functions. So the one that I already showed you, right, here's the one that I already tried to graph before, and you can see that it has some numerical problems. So the program has some numerical problems around the kind of the boundary of the domain, right? It really should be a perfect dome, but it kind of based on the way that it tries to define domains, it can't get a perfect circle that easily. But in any case, you can see this orange dome, and it has the formula square root of 1 minus x squared minus y squared, which is what we discussed before. Okay. All right. Now let's do something a little bit more complicated. Okay. So we have the function. Our function in this case is y times quantity y minus 1 times sine of pi x. Right, so this is a function. Now we're starting to mix things that are quadratic and trig functions. Okay, And so let's just go ahead and think about what the slices through these functions look like. All right, so go back. Now we have this plane, right, that we can use for slices. This looks like it's going to be a little more complicated than the other function, but let's go back to the formula and think about it, right? Think about it algebraically. If I plug in a fixed value of x, right, my sine pi x term is just a constant, and what I have left is a quadratic function, y times y minus 1, right, times quantity y minus 1, and then it's just weighted by whatever the value of sine pi x is. So in general, these should be, right, these should be quadratic functions. And if you look, as I go ahead and vary where I take the slice, no matter where I stop, right, no matter where I stop, I actually get a quadratic function. Even though this graph looks very complicated, right, its slices can be very simple. All right, well now let's switch, instead of taking slices through, right, slices in x, let's take slices in y. Now, algebraically, if I look at this, if I plug in a fixed value of y, I should get something times sine pi x. And so I expect that all of the slices going this way should look like sine functions. And so you can see that each of them is sine function with a different amplitude, possibly 0, right? There are two values where the function just kind of collapses to 0. And those are when n is equal to 0 and when n is equal to 1. And you can kind of confirm that here. All right, but all of the other slices are just sine functions with some weight that's determined by the value of y times y minus 1. Right? All right, and then let's go, right, so let's go back to to our whiteboard and right, so fixing one variable, we're going to call this, right, we're going to call this slicing. Okay, we're going to call this slicing. Now, and by fixing one variable, I mean one independent variable. On the other hand, I can think about fixing the independent, or sorry, the dependent variable. Which is z. Now, it doesn't seem like you can do that, right? Because it's the dependent variable. What do we mean by this, right? So, and we're, instead of calling this slicing, we're going to call this a level. And the way to conceptualize this, I think all of us have looked at topographic maps, right? So we've all looked at, say, maps of a mountain, right? And you see that you have maybe the peak of the mountain is here, right? And then you can have all kinds of other, right? All kinds of other shapes. Here we have, say, z is equal to altitude, right? And x and y are latitude and longitude, right? Just to kind of conceptualize it. So we're going to do a similar thing, right? We're going to do a similar thing with our graphs in 3 dimensions, okay? And so the level set of a function f of xy at a given value, z is equal to some constant, right? So this set is the set of all points x and y such that f of xy is equal to a constant. Okay, so that's going to be our definition. Let's go ahead and go back to our graphing software and look at some examples. Okay, so right, let's just go ahead and look at our canyon function here, or sorry, our saddle function here. And now instead of choosing right? Choosing our slice, we're going to choose a level, right? So we'll say z equals n. Here. Doesn't want to give me my slider. I know a trick for that sometimes too. Oh, there we go. I needed to turn the function on. Okay. All right. Now what you can see, right, is that this plane intersects the graph and gives us, right, the line or the curves of intersection are what we would call the level set. In this case, I have the level set at minus 0.8. Now I have the level set at z equals 0, which you can see is just two lines that cross at the origin, right? And I can keep going up. So now I have say the level set at z equals 1. And I define these various kinds of curves. And I'll ask you in a minute to kind of think about what the level sets look like for the fundamental shapes that we just learned. So the saddle shape, the bowl, and the canyon. Okay, but let's also go ahead and look, before we do that, let's have a look at some more complicated functions. So let's go back to, let's go back to our friend that's y times y minus 1 times sine pi x. Okay, and again, now we're not taking slices in x and y, we are taking levels in z, okay? Levels in z, and so as I go ahead and drop the value, you see that I end up with more interesting level sets. So let's go to 2 dimensions and let's actually look at this. Right, let's go ahead and look at this. So now I have a 2-dimensional graph and I have my function. So I no longer have written my function z equals y times y minus 1 times sine pi x. I've set it equal to n. In other words, I've set it equal to my level, right? And you can see as I drop down, so this is exactly like dropping down the altitude, which I was just doing in the other graph. And this point where these circles, right, these little circles came up, let's go back to 3 dimensions and you can see that's exactly the point that I just reached in this graph, right? So up here, those little circles didn't appear. Now I've dropped down, the circles appear, right? If I go to 0, I sort of get like a checkerboard-like pattern, right? And so we can see that in 2 dimensions. Now I have like a checkerboard, more of a checkerboard type pattern. Right, and then back to the circles, and then the circles disappear. Right, so it's the same representation, but we're only looking at the the curve itself rather than both the surface and the cut plane. Okay, and another interesting function. So let's get rid of this function, and we'll try a different function. So the one at the bottom here is 2 minus 2y squared minus 1 minus x quantity, or 1 minus x squared quantity squared, right? So this has a quadratic term in y and a degree 4 term in x. And you can see that I have this function that this one really looks like a mountain with 2 peaks. Okay, so if I take the level set and I come up to the, toward the top, you can see if I were to keep going here, I would get up to the peaks. The value that I've gotten to, which is, in this case, n equals 1, you see you get a level set, that's it's kind of a weird curve, right? It has this cross in the middle. If this were an actual mountain range, you would call this what we call a pass. And also notice that, locally at that point, we have a saddle-like function, right? Whereas we go up to the top of the peaks, we have more of a bowl-like function. Okay, and sometimes, so the way I've shown everything to you now, we can look at this, right? So now I've gotten to this almost like infinity symbol where you have this cross in the middle. So that's my, right? So that's my pass. If n could go a little bit larger, I could get up to the peaks. Actually, let's just go ahead and make that a possibility. Right, so let's just go ahead and change the bounds on the slider so that we can so that we can get up to the top of the mountain. Okay, now this separated into a couple of circle-like functions, right? And at the top, you actually can't see that, but it would actually be just the 2 points, 0, 1, and 0, -1, right? So those are our peaks. All right, so those, right? So that gives us an idea, right? So that gives us an idea about level sets, right? So level sets, some of the shapes we saw are like concentric circles, right? We saw some things with crosses, and then we saw, so in some cases, kind of two, right? So two sets of circles when we went from, so this is the concentric circles here, right? This is the top of the mountain. This is the top of the mountain. This was the pass, and then we had different shapes as we changed the levels. Now it can be hard to put all this together, and QuickGraph isn't actually the best program to look at all of the level sets together. So there's another program that I use, and so you have different modes that you can go in. You can do kind of standard functions, y equals 2x. You can plot in polar, parametric, which we learned before, and here we're doing implicit function. Okay, so I've given this function that has it's like the mountain with 2 peaks, and I've set it equal to a number of levels. Okay, and right, so now we're going to go to the graph, and here you can see all the levels at once. Right, so now we have all the different shapes and coming up to the top of the peaks, right? So this is a good piece of software if you want to look at all of the level sets at the same time. If you like the surfaces, then QuickGraph is really your software. And practice. So right now we're going to do a problem where we're going to think about I'm going to ask you to think about what the level sets look like for the different fundamental shapes, so the bowl, the saddle, and so on, right? And so, you don't necessarily have to worry about drawing them, but you should, if you like, go ahead and back up and look at the surfaces that we've already plotted and think about, think about what the level sets would look like, right? So let's go ahead and give you a question here. So the question is going to ask you to match, right? It's going to ask you to match the bowl function, saddle function, and canyon function to what would be the shapes of their level sets. So your choices are zigzags, lines, parabolas, and ellipses. Okay, so go ahead and give that a try. All right, you may want to go ahead and pause your video while you work on it a bit, and then when you come back, we'll discuss the answers. Okay. All right, welcome back. Hopefully you didn't find that too difficult. Right, so if you went back and looked at the graphs of the functions that we studied, you would see that if a bowl-like function, when you took levels, those levels looked very much like ellipses, right? In fact, they are ellipses. In some cases, there would be circles. So for example, x squared plus y squared would give you a circle. But if you have other weights in front of the x squared and y squared terms, you'll get ellipses of various sizes. Now for the saddle-like shape, you had one degenerate level set that was a cross, but all of the other ones were parabolas, right? Things like 1 minus y squared. And then finally, we had functions that looked like a canyon. You would get lines.